Hello to everyone. In this video, let us discuss crystal field theory and calculation of CFSE. Means what? Crystal field stabilization energy. Okay. First, according to crystal field theory, the bond present between central metal ion and ligand is purely ionic bond. And according to CFT, central metal acts as a cation, or that is called which one? Electron pair acceptor, or we can call it as Lewis acid. And ligands considered as which one? Point charges or dipoles. Ligands considered as point charges or dipoles. Now here, in presence of ligands, now the d orbitals of a metal atom may not have degeneracy for a long time, because here these are considered as point charges are indicated with negative charge. So in presence of that lone pair of electrons or negative charge, the degeneracy of the d orbitals of central metal atom get disturbed. Now, due to that disturbance, there is a splitting of d orbitals takes place. In that, they form two different sets. First one is here dxy, dyz, dzx. These three form a group of sets named as T2G set. And dx square, y square, dz square orbitals form another set known as EG set of orbitals. So like that, in presence of a ligand, when ligand approaches the central metal atom in complex at the time of complex compounds, now what happens here? Degeneracy is disturbed, that d orbitals split into two groups, but that distribution, that means that splitting of d orbitals depends on which one? Means here on the number of ligands approaching and also on the charge present on the cation, that means central metal ion. So these factors can affect the crystal field stabilization energy. So like that, in presence of ligands, now that crystal field splitting we can observe. That means d orbitals will loses their degeneracy and split into two sets of orbitals. Now let us see how the splitting of d orbitals in octahedral complexes. Later we go for tetrahedral complexes. And in case of octahedral complexes, ligands approaches along the which one here? Axis. So in case of octahedral complexes, ligands approaches along which one? Axis. Now in case of central metal atom, the d orbitals which are present along the which one? Axis, or which one here? dx square, y square, dz square. So as the ligands are approaching along the axis, these set of orbitals will feel high repulsion. So then their energy, what happens here? Increases. So this EG set of orbitals energy enhances and T2G set of orbitals energy decreases. So now in absence of ligand, all the d orbitals having degeneracy, these 5 set of orbitals. But in presence of a ligand, now what happens here? Splitting of d orbitals takes place. Here this EG set of orbitals getting high energy, T2G set of orbitals losing energy. Now here this energy enhanced by 0.6 delta naught, where delta naught is called crystal field stabilization energy over octahedral, and here this energy decreased by 0.4 delta naught. So like that, here in presence of ligands in octahedral complexes, now Eg set of orbitals having high energy, T2G set of orbitals having less energy, and this energy gap in between these two orbitals, two set of orbitals, is known as which one? Delta naught, crystal field stabilization energy. Now what are the conditions? Let us see here. First condition is if delta naught greater than P. What is P? Means pairing energy. P is called pairing energy. Pairing energy means after filling T2Z set of orbitals, each with one unpaired electron, pairing will take place. The energy required for that pairing is known as which one? Pairing energy. So the first condition, if delta naught greater than pairing energy. Delta naught greater than means what here? The energy gap in between Eg set and T2G set of orbitals is greater. Whenever when we will see like this means, if a strong ligand approaches the central metal ion, there is a large energy gap between these two set of orbitals. So if a strong ligand approaches means what here? That is low spin complex and diamagnetic in nature. Already in valence bond theory we learnt that if a strong ligand approaches, irrespective to that Hund's rule, pairing of electrons takes place. So like that here, if delta naught greater than pairing energy, in that case no Hund's rule is followed, and that is low spin complex and diamagnetic in nature. That is first condition. And the condition 2 is if delta naught less than pairing energy. That means the energy gap between these two set of orbitals is less. That means which ligand approached the central metal ion means weak ligand. When weak ligand approaches, now that is high spin complex and having paramagnetic nature, and at this time that follows which one? Hund's rule. At this time that follows Hund's rule. So now let us see the configurations for octahedral complex in presence of strong field ligand and also in presence of weak field ligand. So now first let us go for which one here? D1 configuration. Let us see first D1 configuration. D1, first strong field and another one weak field. If strong field ligand is there, we have to which one here? No need to follow that Hund's rule. So first configuration, electrons first we have to write which one? T2Z, then EZ. First electron enter into T2Z orbital. So now configuration T2Z1, EZ0. Weak field also no difference, T2Z1, EZ0. And D2 configuration T2Z2, EZ0. Here also same T2Z2, EZ0. D3 configuration T2Z3, EZ0, T2Z3 and EZ0. But D4 configuration, from this we can get some differences in between strong field and weak field. If strong field ligand is there, already we discussed here, no need to follow that Hund's rule. That means no need to enter that electron in EZ set. Again we have to send that into T2Z. So now configuration T2Z4, EZ0. But in presence of weak field ligand, it follows Hund's rule. So the configuration now becomes T2Z3, EZ1. So like that we have to fill the electrons. And like that if you go for D5 configuration, T2Z5, EZ0, here T2Z3 EZ2. So like that we have to fill the electrons in presence of strong field and presence of weak field ligands. And then calculation of crystal field stabilization energy. So already we have given one hint there that T2Z set of orbitals energy decreases by a factor of 0.4. For each electron, the decrease in energy for T2Z set of orbitals is 0.4. So, now crystal field stabilization energy calculation, number of T2Z electrons into minus 0.4. Next, plus number of Eg electrons into plus 0.6 plus xp, where x is which one? Newly formed pairs. How many pairs are formed? That number we have to write here. If one pair is formed in filling that orbitals, we have to write 1p. While we are filling that T2Z orbitals, if two pairs are formed, we have to write 2p. Okay, now let us see one example here. What is the crystal field stabilization energy of COF6 minus 3? So cobalt F6 minus 3 means cobalt present in plus 3 oxidation state. So now what is its configuration? 4s2 actual configuration 4s2 3d7. But in plus 3 state, we have to remove 3 electrons. So 4s0 3d6. So now the configuration is 3d6. And we know that fluorine is a weak field ligand. Weak field ligand means in this case we have to follow Hund's rule. Therefore, what should be the configuration? First, we have to fill the 3 electrons in T2Z3, then 2 electrons in EZ2. Up to now, only 5 electrons have been completed. Now, 4th electron again enter into T2Z. So, it will become configuration T2Z4 EZ2. T2Z4 EZ2 means here we can draw that structure like this. So, here let it be the T2Z orbital. Let it be the Eg set of orbitals. T2Z4 means 1, 2, 3, 4. Here 2 electrons. That means one pair is newly formed. Therefore, crystal field stabilization energy equals to crystal field stabilization energy equals to what is the formula here? Number of T2Z electrons, how many? 4. So 4 into minus 0.4 plus 2 into 0.6 plus 1p, because one pair is newly formed here. Now what is the calculation? Minus 1.6 plus 1.2 plus 1p. Now this is how much we can get? Minus 0.4 plus 1p. So pairing energy. So like that here we have to calculate which one? Crystal field stabilization energy for COF6 minus 3. Okay, then now we have to see that splitting of d orbitals in tetrahedral complexes. So in a tetrahedral geometry, we know that the ligands approaches the central metal ion in between the axis. So in between the axis means here T2Z set of orbitals dxy, dyz, dzx will feel the more repulsion. So that means these set of orbitals having high energy, Eg set of orbitals having low energy. So now in case of tetrahedral, what is the splitting here? So in presence of ligand, what happens here? Splitting of d orbitals takes place. So T2Z set of orbitals will get more energy and Eg set of orbitals will get less energy, because T2Z set of orbitals present along the in between the axis. So those will get more repulsion. So now see here, in presence of ligands, now T2Z set of orbitals, T2Z set of orbitals will get more energy. This is T2Z. Okay, then come to here another one, which one? Easy set. Easy set orbitals losing energy. Now this energy increased by plus 0.4 delta T, T for tetrahedral, and this energy decreased by minus 0.6, minus 0.6 delta T, here plus 0.4 delta T. So this is splitting in case of which one? That tetrahedral. In this also the same story. Now for an example, one question I will give here. What is that question? For example, some X element are forming a complex compound having tetrahedral geometry, and its configuration is D4. Its configuration is D4, and the question they have given like this: if delta T greater than pairing energy, if delta T greater than pairing energy, what is its configuration? So as delta T greater than pairing energy means that is a strong field ligand. So no need to follow Hund's rule. Therefore, we have to fill that 4 electrons in easy orbitals only. No need to go to T2Z. Therefore, the configuration is which one? Easy 4, T2Z 0. If the same question, if delta T less than pairing energy is given, as delta T is less than pairing energy means that is weak field ligand. So we have to follow Hund's rule. At that time this configuration will become what here? EZ2 T2Z2. So like that we have to write the configurations for which one that depend upon whether the complex is octahedral or tetrahedral, and also we have to consider this phenomena also, whether delta T greater than pairing energy or delta T less than pairing energy. Now the relation between delta T and delta O, that means crystal field stabilization energy in tetrahedral and in octahedral. So what is the relation? See here, delta T equals to 4/9 delta naught, 4/9 delta naught. So in recent examination, one question they have given. What is that question? Crystal field stabilization energy of COF6 minus 4 is 18,000 some calories or something in any units they have given. Now what is the CFSE for COF4 minus 4? Now that means here 6 ligands approached means this energy belongs to which one? Delta naught. And here we have to calculate the crystal field stabilization energy of this complex. Here 4 ligands are there means it is tetrahedral geometry. So now we have to use this formula. That means delta T equals to 4/9 into 18,000. So 9 ones are 9 twos are. We get which one? 8,000. So like that we have to calculate delta T using delta naught. And what is the order of CFSE in different complexes? So first, delta square planar greater than delta octahedral greater than delta tetrahedral. So this is the sequence of which one? Crystal field stabilization energy of different complexes. Okay, now let us see one question here. How to write the electronic configuration as per crystal field theory. So now the configuration we can get like this here. For example, CONH3 taken 6 plus 2, they have given plus 2. Now, what is the electronic configuration as per crystal field theory? They give the question. First, we have to calculate its oxidation number, cobalt plus 2. So, configuration 4s0 3d7. So, 3d7 is the configuration we have to write as per CFT. So, first, we have to see that is it tetrahedral or octahedral geometry, means as 6 ligands are approached, it is octahedral. Octahedral geometry means first electrons enter into T2Z, then only electrons enter the EZ. So we have to arrange like this T2Z and EZ. First we have to decide in which electrons should enter first. That means either into T2Z or into EZ. As it is octahedral complex, first electron should enter into T2Z, then only they enter into EZ. That is the first clarity we have to get. Then second clarification regarding the ligand. See towards the ligand. It is weak or strong ligand, we have to observe. Ammonia is a strong ligand. Ammonia strong ligand means no need to follow that Hund's rule. That means first we have to fill T2Z completely, then only we have to write the another electron in EZ. So we know that a T2Z set contains total 3 orbitals in that set. So maximum 6 electrons one can fill. So now out of the 7, T2Z get 6 and send that one electron to EZ orbital. Now this is the configuration. That means now EZ1. So T2Z6, EZ1. This is the configuration for which one? D7, 3D7 configuration. For example, instead of this strong ligand, if any weak ligand is approached, that at that time the same 3D7 configuration we have to follow the Hund's rule in presence of weak ligand. That means first we have to fill 3 electrons in T2Z, then 2 electrons in EZ, then the remaining electrons should come into T2Z. That means first T2Z3, EZ2. Already 3 plus 2, 5 electrons are filled. Still we have to fill 2 electrons. Again start filling in T2Z. Therefore we can get T2Z5, EZ2 configuration. So this is the difference between strong field and weak field ligands. And after writing this, we can calculate which one, that crystal field stabilization energy. So in this case, crystal field stabilization energy is equals to, here T2Z6 means 6 into minus 0.4 plus 1 into 0.6. 6 4 is 24 means minus 2.4 plus 0.6. So we can get how much here? Minus 1.8. That is the crystal field stabilization energy calculation. So this is regarding crystal field theory. Okay, in our next video, let us go for which one? Isomerism. Okay, right. Bye.